later pursued postdoctoral research at both the University of Salerno and then at Aarhus University. Her research primarily focuses on multi-party computation with a strong emphasis on foundational aspects. Additionally, she has a keen interest in zero-knowledge proofs and their applications. So please join me in welcoming Louisa. Thank you.
Thanks a lot for the introduction, and thanks for this invitation. I am very excited to be here. So let's start. We are going to talk about non-malleable protocol and their relation to cost and round MPC protocols. So let me set up a bit the stage. Here we are talking about a very specific setting. I want to be very, very restrictive in the type of assumption that I want to make to construct my MPC protocol. So the first restriction is that I don't want to use any setup, so no CRFs, and not heuristic assumption. So no random oracle. Second, we are in the dishonesty majority setting. It means everybody except one party can be corrupted by the adversary. And then the Cleave's result says us that in this setting, the best guarantee that we could achieve are unanimous abort or identifiable abort. Furthermore, I am interested in constructing this protocol from the least possible number of assumptions possible and from polynomial time assumption. The protocol should be secure in the real ideal world paradigm, in particular with a simulator that makes black box access to the adversary. So that's the setting we are interested in, and we are interested on how to construct cost-around protocol in this setting. So in particular, that's the roadmap that we have ahead of us. I am going to attempt how to design a round optimal protocol for coin flipping, just for the coin flipping functionality. And then I am going to slowly introduce some non-malleable protocols, starting from non-malleable commitment, going to non-malleable zero knowledge. And then at that point, we are designing our round optimal coin flipping protocol. And then I will just briefly talk about how these non-malleable protocols relates to cost and round MPC protocol. And then, based on the time, I want to talk about a specific non-malleable construction, a specific construction of malleable zero knowledge. Okay, so let's start attempting our coin flipping protocol. So these are our three parties, and now a simple idea to construct coin flipping is that the first part commits, and only when everybody gets this message, the second party commits. And then, sequentially, after everybody got this message, the third party commit. And then they are also going to open this commit sequentially, which means that the first party open. When this opening is received, then the second party opens. And only after that, the third party opens. So this protocol is not simulation-based secure, but we can already claim that the input of the parties are independent. In particular, let's consider just one adversary, and the message committed by the adversary, the message R2, is independent from the commitment of R3, because when the adversary commits, there is no R3 in the view of the adversary. So it's completely independent. There is no way you can guess this bit. You can only guess the bit. Okay? Moreover, this commitment of P2 is computationally indistinguishable, is computationally independent from R1, and one can show this with a simple reduction to the hiding of the commitment. And this is crucially possible because we open R2, so if R2 is somehow related with R1, I can just use R2 to break the hiding property of R1. But not crucially that to design those type of protocol in this way, we are going to need a number of rounds that is proportional to the number of parties. Like the argument that I just showed about independence of the inputs crucially relies on the fact that we are opening the commit sequentially and we are committing sequentially. So I want to design constant round protocols. So I am a bit unsatisfied with this approach. Let's see what happens if we are committing all at the same time. So now the commitment happens all together, and the opening happens all together. So what goes wrong in this case if just one part is corrupted? Well, the adversary in this scenario is rushing, which means that in one round, he could just wait from the commitment of the other parties before generating his commitment, which means that he can wait for this commitment, plays a bit with it, and commit to a function of the input of the other party. Note that at this point, for doing this type of attack, the adversary doesn't need to know what is inside the commitment, but is just tampering with them. Think about a commitment that has homomorphic property. Then you can giving a commitment, you can re-randomize those commitments. This is completely allowed, and the commitment is still hiding. So that's not a problem, that's not a property that is related to the hiding of the commitment. This type of attack are not covered from a commitment, which can be hiding and homomorphic. So we need an additional property. In particular, in this setting, the adversary can just set always the coin flipping to be 0 if he tampers in certain way with the commitment. So we need something more. We need, let's just think intuitively. We want that when the adversary commits, he commits to a message that is unrelated to the commitment that is receiving from the other parties. So in particular, we want to have what is called non-malleable commitment. So in a non-malleable commitment setting, the adversary is also called the man in the middle. Because if we think about our coin flipping idea, he is first receiving the commitment from the sender, and then he's producing a commitment on his own, so he's actually acting as a sender with the receiver. Okay? So just some notation. In the interaction between the sender and the receiver, between the sender and the man in the middle, is usually called the left session interaction. And the interaction where the man in the middle acts as a sender is called the right session, just because it's possible that during the explanation I'm going to use these terms. Okay? So what we want to have here, we want to have that the commitment of the message in the left session is unrelated to the commitment that the man in the middle is producing in the right session. Okay? So that's intuitively what we want to have. But now we need a formal definition of those properties. How are we going to map this in a formal definition? So let me guide this through to you. So it's very similar to the hiding game. So we have two experiments, exactly as the hiding game. But now we want to map an additional property. We want to say, oh, the message on the right is unrelated to the message on the left. So how are we going to do that? Well, we are going to keep our distinguisher that distinguishes these two games with the message committed by the man in the middle. So the distinguisher now has also an input, whatever the man in the middle commits in the right session. So if this message, and then he has to distinguish, is the sender committing to M0 or is the sender committing to M1? Now, if M0 prime or M1 prime has a relation with M0 or M1, he can easily distinguish. So when a commitment is non-malleable, the distinguishing advantages between these two games become negligible. So that's the notion of non-malleable commitment. And so it's basically formalized with the man in the middle that does the execution, and then there is a distinguisher that wants to distinguish these two games. Very importantly here, we are omitting the fact that the man in the middle can just copy everything. But this, in the formal definition, this is handled. But for now, for this talk, let's just say that the man in the middle cannot copy. So in this setting, I am talking just about one receiver. But if we think about MPC protocol, when there are multiple parties, actually the adversary talks with multiple people. So in this setting, we have actually multiple, especially if we are using point-to-point channel, we have actually multiple receivers. So in this setting, there is the sender that is committing to MB, and now the adversary can generate multiple commitments in the right session. And now one is wondering, okay, why stressing about that there is a second setting when we have multiple receivers? Well, it's because actually a non-malleable commitment scheme that is secured with respect to one receiver, it's not straightforward that this is also secure when we have multiple receivers. Actually, it's possible to show that a scheme that is secure in the 1-1 setting is actually completely insecure when we plug it in and there are multiple sessions. So this also tells us that these objects are not composable for free. And that's related to the fact that we are in the plane model, and the way usually the security of this object is proven is truth rewind, which makes a bit more difficult, I would say, to prove the security when multiple objects are played in parallel. So just giving intuitively you the idea why a 1-1 non-malleable commitment is not also one many, well, that's because the adversary can just, in the single session, can just commit to something that is completely unrelated. It can just commit to a share of a random share. And then only when we look at all messages together, then we can map the relation that they have with the initial message. For instance, this can be all shares of MB. So now we have our non-malleable commitment. So let's see if we can build now a coin flipping protocol. Well, the optimal round complexity of coin flipping in the plane model, with all these characteristics that I am saying here, is 4 rounds. So now the problem really boils down on how many rounds we can construct those commitments. So if the commitment does not have a non-malleable property, then you can construct commitment in 1 round. So now, is it the same when you add this non-malleability property? Actually, when you are in the plane model, this commitment needs at least 3 rounds. So they cannot be constructed in a non-interactive way. If you add a CRS or a random oracle, then they become non-interactive. But if you remove those assumptions, then they require some round of interaction. So these are interactive primitives. And I want to just give you an overview of how much time is required to have an optimal round complexity for those type of protocols. Like the first construction by Dolev, Dwork, Naor, that also introduced this concept, had the logarithmic number of rounds. And then there were many, many results that aimed to construct an optimal round protocol. And in particular, we can see that very recently, we have a 3-round construction. And we can also see that some of them are secure in the concurrent setting, meaning when there are multiple receivers. But if we want to aim for one-way permutation only, actually, this construction are still secure only in the with the respect to only one receiver. So now the question is, which one do we use for constructing our coin flipping protocol? So what I want to do in this talk is to be very minimal in terms of assumption. So we don't want to go from number theoretic assumption, and we are instead using the one that are from a one-way permutation only. But as I was saying, this is secure only in the one-one setting, while for MPC, usually we interact with multiple parties at the same time. So how we are going to solve this problem? Well, we are going to solve this problem using those non-malleable commitments to construct a new non-malleable protocol. In particular, we want to construct now, exploiting the non-malleable commitment, something called non-malleable zero knowledge. How we are going to do that? OK, let me first introduce what is non-malleable zero knowledge. So very intuitively, it's a zero knowledge proof, as we know, but it has an additional property. Well, which is that the adversary, even receiving simulated proof, he can still not tamper with it and giving simulated proof on the right session. So let me be more specific. So let's start with just the definition of zero knowledge proof. So what is a zero knowledge proof? It's a two-party protocol between a prover and a verifier. Now the prover wants to prove that some statement is true. And if both parties are honest, at the end of the protocol, the verifier will accept this computation. Moreover, there is a second requirement that is soundness, which says that a malicious prover cannot fool an honest verifier. So the verifier is going to accept only when the statement is true. And finally, we have the zero knowledge property, which intuitively says that the malicious verifier cannot infer any information about the witness. And the way this is modeled is with the ideal real-world paradigm, where in the real world, the adversary is interacting with the prover, and then we have a simulator that is interacting with the verifier, and it is producing a view that is indistinguishable from the one of the real world. Okay? Until now, it's only zero knowledge, that as we know. And now we are going to require an additional property that is non-malleability. So what do we want to capture in this setting? Well, we want to capture this scenario. There is the prover that interacts now with the man in the middle. And the man in the middle has also the capability to produce a proof on his own. Let's remember before that our adversary can be rushing. So he can look at the zero knowledge of an honest party and then produce its zero knowledge. And we want to claim that the zero knowledge of the adversary is still for a true statement. The soundness is not violating also in this setting. How are we going to do that? Well, we can define a second game where the simulator internally acting with the verifier, as in the case of zero knowledge. For now, it's just zero knowledge. But then the simulator is also interacting with the verifier. And we are going to say that in the ideal world, the probability that he is proving a false statement is negligible. And now, since these two games are indistinguishable, then that should be true also in the real world. For those of you familiar with the notion of simulation exactability, what I am saying here is slightly weaker. So just to recap, when the zero knowledge is also non-malleable, it means that the man in the middle, only with even if he is receiving simulated proof, he can produce a simulated proof for a false statement with a very low probability. Okay? So that's the notion of non-malleable zero knowledge. And now I want to give a very high-level construction to demonstrate that these two objects that I am talking about are very related to one another. In particular, the prover can commit to the witness of a non-malleable commitment, and then is going to prove that this non-malleable commitment contains a witness for X in L. And it's going to do that using a normal zero-knowledge proof. So non-malleable commitment plus zero-knowledge gives you non-malleable zero-knowledge. That's the takeaway. And at a very high level, what is the reason is that because the non-malleable commitment is handling all the type of non-malleable, all the type of tampering, and the soundness of the zero-knowledge guarantees that the commitment is well-formed. So one comment about this construction is that these two blocks need to go one after the other. And this is because, as I was saying, this, in the plane model, composability is not given for free. So if we execute them in parallel, well, we need extra machinery, and we need to be extra careful to actually playing them all together. Indeed, to reach the optimal round complexity on a malleable zero-knowledge protocol, it was a result of 2014, and by Goyal et al. And basically, I don't want to go into the details of the construction, but they carefully align those primitives, and they have a proof that these two primitives can play in parallel, and they can reach the optimal round complexity, which is 4, which is the same lower bound that holds for zero-knowledge. Okay? So now, finally, we arrive at the point that we have our non-malleable zero-knowledge. How are we going to construct a coin flipping at this point? Well, there is just at a very high level, what is happening is that the prover commits twice with a binding commitment, just a normal commitment, which for technical reasons that I am not going through, but is also extractable. Okay? And then, so this is the first 3 rounds of the protocol. This already covers 3 of my round of the protocol. And now, in the last round, I am not opening this commitment, but the party is just sending the message R1. And now, what we are going to add is a non-malleable zero-knowledge proof. This non-malleable zero-knowledge proof ensures me that party P1 is committing correctly to the message that is opening in the last round, and that these commitments are both well-formed. Okay? And party P2 is going to do the same. Now I just described it for one party, and this is easily extendable when there are multiple parties. So what is the idea here? Why this protocol becomes secure? And we don't have anymore the problem of tampering with the commitment. Well, it's because any tamper of the commitment can be translated into an attack to a non-malleable zero-knowledge. Any possible tampering can be related to the non-malleable zero-knowledge, because the statement of the non-malleable zero-knowledge is proving that the two commitments are well-formed. So just one additional caveat here is that the actual statement of the zero-knowledge is available only in the 3rd round, because the commitments are completely defined only in the 3rd round. And actually, R1 is sent in the last round. So we are going to need that this non-malleable zero-knowledge needs an extra property that is called a delayed input, which means that the statement is used just to construct the last round of this protocol. So that's at a very high level how non-malleable protocol, because here we are using a non-malleable commitment and then using that and constructing a non-malleable zero-knowledge, how those primitives can actually help us to construct constant round protocol, in particular round optimal protocol. So, and that's not the case only for coin flipping. If we analyze the round complexity of a constant round MPC protocol, I mean, here there is a lot of result. We don't need to know all of them. Very briefly, by now we know what is the optimal round complexity of MPC protocol in this setting. It's 4 rounds, and we know them from various assumptions, even using black box use of the primitive. So this is just an overview. Okay, but the only interesting thing that I want to stress for this talk is that all this result came at the same time or after that we knew what was the optimal, that we knew that there was a 3-round non-malleable commitment, that there was a non-malleable zero knowledge. And now, if you dig a bit in how they are constructing them, I am not going into details of that. But if you just, at high level, want to see which primitives they are using, where they are all using a non-malleable protocols. Okay? In particular, all the results that are non-black box in the use of the primitives, they are using a non-malleable zero knowledge or a non-malleable commitment. All of them. So the relation between these two things becomes very tight. And well, the one that use black box use of the primitives, they cannot really use zero knowledge because then it's white box in the use of the primitives, okay? So they use one other thing that is called a non-malleable privilege transfer, but I will not go into the details. I felt that the third primitive was a bit too much. So instead, what I want to focus on is to give a construction of a non-malleable zero knowledge. Can you tell me what is more or less the time?
You're 25 minutes.
Okay, thank you. Okay, so let's construct a non-malleable zero knowledge protocol. In particular, I want to construct a non-malleable zero knowledge protocol. That's the line of work for round optimal non-malleable zero knowledge protocol. And it looks similar to the one of the malleable commitment because these two things are very related. So, and we knew that the optimal round complexity was 4. So, but now what Kim et al. Observed was that, well, these type of construction are round efficient, but they are very far to be computational efficient. The way they were constructed was very difficult to run them and obtain a result in few seconds or in few milliseconds. So they are like, they observed, they asked the question, can we have them practical? Can we actually execute them on a machine? And so they give a first construction, which was more than 20 rounds, but it was actually practical. You can actually execute it. And the result was for mini-crypt assumption, because they want that these are holding also for post-quantum security. So we kind of improved on the result, giving one that is in 9 rounds, so with a better round complexity, with a better efficiency, and still relying on mini-crypt. But at this point, we want also to rely on them in a black box way. So just to maybe a brief note, black box means that we want to use only the input-output behavior of the primitives and not relying on their code. So I am going to go in some details of this construction. And to do so, let's first observe why the trivial, now we don't care anymore about round optimality. So the first observation can be why we don't use the construction that I was telling in the beginning. Why this is not efficient or black box. Well, there is a big drawback here, is that to prove this statement, I most likely need an NP reduction, which is extremely expensive and also makes everything non-black box, because I am going to need how the actual non-malleable commitment is constructed. I cannot use it as just one box. So this is not is really especially for this problem, is really inefficient. So I want to use, I want to avoid NP reduction. And what we do we want to avoid NP reduction, we use sigma protocols. And so just briefly, what is a sigma protocol? It's a 3-round move protocol, which is where the prover, again, wants to prove some statement to a verifier. Completeness means that the verifier is accepting, but then, a true statement, but then we have other two properties. The first one is special soundness, which says that if I have the same first round, but two accepting transcript for different challenge, then I am going to extract the witness. And also is equipped with a very weak form of zero knowledge, because if I know, if this, for some random challenge, the simulator can generate a transcript that is indistinguishable from the one of the real world. But here is crucial that the challenge is known in advance, okay? So to run this simulator, I need to know the challenge in advance. So this is the main building block of this construction, and then we are gonna need, of course, a non-malleable commitment. And well, this non-malleable commitment has also an extra property, which is extractable. It means that when I can run an extractor, talking with some sender and some malicious sender, and I am going to extract the committed message in some polynomial time. So I am also going to need this property, and that's all I need. How this protocol is constructed? Well, so I have my prover, I have my verifier. So what the prover is doing is going to generate the first round of the sigma protocol. Now the verifier commits to a challenge, a random challenge. And then the prover is sending also a random challenge. And now the verifier is opening his challenge, and they are computing a coin flip. So, and now the coin flip is the input to generate the challenge for my third round of the sigma protocol. And I am going to send this third round. So the verifier is going to accept if the transcript AC zeta is accepting. So here, what I am doing is basically running a sigma protocol where the challenge of this sigma protocol is generated to the coin flipping using a non-malleable commit. So now what I want to go slightly details in is how we prove non-malleability of this object. Okay? Because this construction seems quite easy. And at least what I think usually of those type of protocol is that the major difficulty relies actually on how you can prove that the entire scheme is still secure. How non-malleability actually holds. So let's start from the real game, and let's see how the simulator works and how normal soundness is proven. So the simulator, intuitively, what we want to have is that he knows the challenge of the sigma protocol in advance. So it's going to pick a random challenge, pretend to be lucky, and sending A. Now, the man in the middle is, the adversary, sorry, here is a verifier, is generating C0. And now the simulator, using the extractor, can actually extract C0. And at this point, he has all the information to generate a correct C1 star. So he can cast the coin flipping as he wants. If he can cast the coin flipping as he wants, he can send C1 star, the man in the middle opens C0, and then he can freely send zeta. So this is the simulator. Now, how we are going to prove that this scheme is sound? Well, intuitively, here is still, the sigma protocol is still very useful. I need to rely just on the two special soundness of the sigma protocol. So how I am going to do that? Well, I have my first transcript from an execution between the simulator and the man in the middle. So I collect my C prime, and I collect my first accepting transcript. Now I am going to need a second accepting transcript. How I can generate this second accepting transcript? Well, I am going to rewind and send this is still there, and I am going to send a different challenge to the man in the middle. So, and this is going to answer me in some way. And at this point, I collect zeta, and I have my second transcript. Now, notice that from this true transcript, I can extract the witness. But this is true only when the challenges are different. So I need to prove that the coin flipping is unbiased. At this point in time, I can just rely on the hiding of the commitment. Just very similar as I was explaining in the beginning. Here you can still rely on the hiding of the commitment because this is just one session between the prover, between the malicious prover and the verifier. So for now, what we prove is the first part. We prove that this scheme is zero knowledge and that soundness holds in the real world. Now what I want to prove is that soundness also holds in the ideal world. But now in the ideal world, the man in the middle is interacting with the simulator and not with the real prover anymore. In particular, he's interacting with an object that does not know the witness. So how are we going to do that? So this is the scenario of the ideal world. There is my simulator, and there is the verifier, the honest verifier in the right session. So we are starting executing the simulator. He sends A. He gets a commitment. He's extracting. The simulation continues as I was explaining before. He gives C1 star. And now we can generate zero. OK. And now, at this point, we want to prove that also this session is for a statement for X in L. We want to prove that the man in the middle is not fooling an honest verifier. And now the intuition is that, we can do just as before, right? Before we extract two transcripts, and we extracted the witness. So why not just do the same? So we are going to rewind. But now notice that when we are rewinding also the session on the left. So here, in particular, this commitment of the honest verifier and the one of the man in the middle at this point can be related. And in particular, when we want to construct, we want to rely on the special soundness. So we want to really say that these two messages are different. We want to say that C prime is different from C hat. But now what the man in the middle can do is just mole whatever is receiving, such that the result of the coin flipping stays always the same. So in the simulated world, since the simulator casts one challenge as he wants, the man in the middle can just do the same, can just replicate whatever the simulator does. So now, to claim that this is not the case, well, we need to rely on the malleability and on the non-malleability of this object. But note here that the entire tampering attack is obtained only when I have C1 hat. This is the point where the final attack is performed. But notice that this message is generated by the man in the middle only after he sees this message, which in particular means that I have to extract to generate this message in this particular way. So if we are doing a simple reduction to non-malleability, this is not going to work because this reduction wants at a point to rewind the challenger of the non-malleable commitment. Okay? So since we are rewinding by since we are extracting by rewinding, sorry, this extraction will rewind the man in the middle, which will rewind the challenger of the my protocol. So I cannot perform this reduction in a very straightforward manner. Okay? And this is exactly the problem that I was going to say, that these primitives, since they are rewindable secure, they are not composable for free. This is exactly the type of problem that one can encounter. Rewinding causes rewinding of the man in the middle, which are difficult to handle. Indeed, we need to craft really this reduction in a more careful way. So at a very high level, sweeping a lot of things under the rug, we are going to construct a two-phase reduction. In the first phase, I am going to go with constructing a man in the middle for the non-malleable commitment, exploiting the man in the middle from the non-malleable zero knowledge, and then I am going to build a distinguisher for my non-malleable commitment. So how the man in the middle is going to work? Well, so we are assuming by contradiction that there exists a C prime, that the man in the middle is always casting. So since this C prime is there exists, we can actually run just the man in the middle with this value built in. Okay? So, and this is my adversary from the zero knowledge, and now I need to exhibit a non-malleable commitment, a man in the middle for non-malleable commitment. So what I am going to do is to generate two random messages and just cast the challenger for these two random messages. And now the challenge is going to commit to one of the two. And now my man in the middle for the non-malleable commitment is just acting as a proxy between the two sessions. So the reduction for now is very easy. My man in the middle is just performing the same action of the non-malleable zero knowledge, man in the middle, one-to-one mapping. So until now, the phase one is very easy. So now we have our man in the middle. Now the problem comes at the next message. We cannot really generate the next message. So how are we going to do? Well, we are going to exploit the actual definition of the malleable commitment and use instead a distinguisher. So the distinguisher, by definition, takes the entire view of the man in the middle and takes the message committed by the man in the middle. So at this point, he knew K0, and he can just resume the computation at this exact point. So the computation of the man in the middle finishes here. Now the distinguisher recreates everything. And at this point, he know how to compute C1 star. So he can send C1 star and generate C1 hat. Once he obtains C1 hat, well, we knew that with high probability this is equal to C prime. So, well, he can just guess MB. Because MB, by contradiction, is actually this value. So he can just guess the message, if the message committed by the challenge is M0 or M1. So there are some details on this, especially to claim that the advantage of this reduction is not cancelled out, but I am gonna, feel free to ask me offline, okay? So, but at high level, that's the reduction. I am gonna use the distinguisher to see which one is the message committed by the man in the middle. Okay, so this is our funnel protocol. For now, we are all happy that it works. I hope that we are all happy that it works. So what is the bottleneck here? Well, the bottleneck is actually that this still is inefficient. The only constructor that is efficient, it relies on number theoretic assumption. So what we actually use is in the construction is something weaker, which makes the reduction a bit different from what I showed you a bit more complicated on the one that I showed you. Okay? But everything is still working. And basically, the weakening property is that the man in the middle can just commit to valid message. So he cannot commit to both. He cannot commit to invalid message. So at this point, we lose extractability for this. This object is very efficient. It's from black box use of one-way permutation, but we lose extractability. So what we show in the paper is that adding a 3-round non-malleable commitment on top makes this still efficient and also extractable, and also weak non-malleable. Okay? So the final, this is the main takeaway is that the final construction is using a slightly different object to the one that I showed you, and this is mainly because we want, in this case, we want to be really efficient. So, well, just as a summary, this can be used with any Sigma protocol, and it's practical. So concluding, this is the current state of the art on the malleable zero-knowledge protocols, and I hope I convinced you by now that these are very important when you are in the plane model and you want to construct cost-around protocol. My focus was on MPC protocol, but actually this can be used in other scenarios. So some question that I find interesting, well, I find actually interesting that we still really don't know how to construct that with concurrent security from one-way permutation. There is actually no optimal construction that is concurrent secure and is minimal in terms of assumption. I also would like to see more work that improve efficiencies of these objects that are very minimal in the terms of assumption that they are using. And finally, there is a recent line of works that focus on a man in the middle that is also quantum. It focuses on quantum man in the middle. And there is a constant round protocol in this setting, but it's not optimal. And that concludes my talk. Thank you.
Hello. Thank you, Luisa, for a wonderful talk. Can we take some questions at this time? Are there questions from the audience? I think Yash has a question. Thanks.
Yeah, thanks for the nice talk. So you may have explained it, but I missed it. But one of the constructions earlier, I think either the zero knowledge or the coin flipping one, there was, I think, where you had to commit to the same bit twice and then prove that they're the same. Why do you have to?
That's a great question. It's needed in the proof because it's like we need these two commitments to be extracted. So you need to extract in the third round. And now in the proof you are making 1 to 0, but you want to still commit to the one, to the other one. You are using a this intrinsically is a WI proof. This is two commitment, and I attach a WI proof to making them extractable. So when I want, and then I need two witnesses to. So the actual construction is commitment of R0, commitment of R0 again, and then I have a WI proof that proves that these commitments are commitment of the same message to make them extractable. And so I am going to need two witnesses to do that. So I am adding a second commitment.
But the second, isn't the witness the same for both?
No, it's the opening of the commitment that is. Yeah.
Thanks.
It's basically to making them extractable, but also rewindable secure. That's that's the explanation. Yeah.
Thank you. I believe we have time for maybe one more question. Someone has a hand up over here.
I just want to clarify. So the GR19 protocol is it works from one-way permutations and has 3 rounds.
Which one?
The GR19.
Yeah.
So what is the missing step there for a round optimal construction?
It's secure only in the 1-1 setting. So only against one receiver, not in the concurrent setting. And this is not, and the concurrent setting, the 1-1 setting does not imply the concurrent setting.
Yeah, and it's probably going to be hard, right, with that protocol?
Yeah, I think so, yeah.
Thank you all very much. Please join me in thanking Luisa again.
Thank you. Thank you.
And now I hope you'll all join me in welcoming the wonderful Karmit Hazai to give us a talk, or in just a moment, I believe she's making her preparations. But while she's doing so, let me introduce her. So, Karmit Hazai is a professor in the Faculty of Engineering, Bar-Ilan University, Israel, and a co-founder of Ligero Incorporated. She received her PhD from Bar-Ilan University in 2009 and was a postdoctoral researcher at the Weizmann Institute of Science and Reichman University, Israel, and Aarhus University, Denmark. Karmit's research lies in the foundations of cryptography, with a special focus on secure computation and zero-knowledge proof systems, both in theory and in practice. She co-authors the book Efficient Secure Two-Party Protocols, Techniques and Constructions. She was program co-chair of Eurocrypt 2023 and won the Distinguished Paper Award of CCS 23. So please join me in welcoming Karmit Hazai.
Thank you. Thank you for the introduction. Hi, everyone. Great to be here. Thank you for the organizers for having a really wonderful event. I can't imagine a better place to start the journey of TPMPC outside of Europe. Okay, so in this venue, I already gave some talks, but this time it is a little bit different, because I'm going to not just describe or talk about my academic research, but I'm also going to tell you how we in the company are implementing this research, making it not just practical, but as a platform that can be used by other people. So to start, I want to give you to start with Nigel's quote from Eurocrypt 17. Which Nigel is here in his spirit. He's also one of the fathers of this community, and this is something that is this quote is also something that I feel reflects how I feel. Right, the theoretician thinks I'm a practitioner. Practitioner thinks I'm a theoretician, and me, maybe others think I am. Do you think what he said in the conference? Anyone? Think Nigel. Yeah, he said, I think I am a fraud. Okay, so I don't think I'm a fraud. I think I'm an educator. I think part of doing this research as part of like an academic environment is very nice, is very good. But making these tools accessible outside for more broad, I would say, communities that can actually use those tools and build zero-knowledge apps, I think is as important as advancing science, because we got used to use crypto in the context of protecting data, right? And privacy and verifiability are two values that are very, very important in protecting data. At this point, there are many, many tools off the shelf, standards, people can use them, and this is great, right? But what about protecting computation? So in theory, we know how to do it, right? And a large part of this venue is about these tools. We have MPC, we have ZK, we have FHE, and this is great. But what about in practice? And I'm not just talking about implementing these tools. This is not just about running times. This is much more beyond that. This is how to deploy, how to make this knowledge accessible, how to bridge the gap between how to protect data, and how to protect computation. And in this talk, I want to tell you about our vision at Ligero. Our vision is about building, right? We view zero knowledge as a privacy tool. And our vision for building both useful and usable privacy tools, I will tell you exactly what we mean by useful and usable. But not only that, we want the cost to be zero. So what do I mean by that? So just imagine that the ZK prover cost goes to zero. That could be wonderful, right? We could prove quickly and privately and cheaply from anywhere. But I want to stress, what I mean by zero cost is basically zero additional cost. So there is some cost to run a computation, right? We want the ability to prove something privately to be as much as free, right? The additional cost of adding those, our privacy tools cost practically nothing. And that means that we're aiming to run these tools from any device, laptop, cell phone, tablet, Blueberry Pi, anything, right? This is the goal. And in some sense, it follows the philosophy of the original, the paper that started this journey of zero knowledge, right? The original paper by Shafi, Silvio, and Charles Rakoff. If you read the paper, that they say that zero knowledge is defined as a proof that convey no additional knowledge. So there is some knowledge that is learned by the proof. Then the goal is to not learn any additional knowledge. And in that sense, this is what we're saying. We want the cost or the proof to not add any additional cost. So it will be as minimal as possible. Okay, and why should we care if the zero knowledge prover goes to zero? That speaks for itself, right? We have really, really wonderful applications that we can that can benefit from having such efficient tools. I'm going to list just a few, right? But there are plenty that you can think of. For instance, proving an inference of a private AI model, and we really want it to be in real time, in seconds. Verifiable credentials, right? This is a client-side proving. Just imagine that you want to log into a website and you need to prove something about your credentials. You don't want to hand them. You don't want the information, the data, to leave your computer. You want to prove something of that, and this should be real time, right? Privacy preserving regulatory compliance financial systems, right? All financial systems, especially in the transition from Web 2 to Web 3, where we want to do a lot of the computations off-chain, right? Right now, it's not really scalable unless we throw a huge amount of hardware. And yeah, that goes to limitless blockchain scalability. Okay, in this context, there is a quote by Vitalik that is relevant to our discussion. This is from last September. And he's saying that privacy use cases require client-side proving. Currently, client-side provers are just not fast enough for anything beyond Merkle branches. So this is where we are right now. And our goal is to challenge this status quo. Our goal is to develop client-side technology, okay, that can be actually deployed in real time. And let me make a bold prediction. We would like to be in a place by the end of 2025 when we can have a real-time LLM inference from a browser. That means billions of gates proven in real time in matter of seconds from a browser. So this is our prediction. This is what we're aiming towards the end of 2025 at Ligero. Okay, let me, I want to show you a very short demo. And it is so simple that even theoreticians can do that. So let me see, how can I switch? Yeah, how can I switch to Windows? Yeah, it's this one. No, Chrome. Yes. Oh, okay, great. So this is our website. Yeah, but I need it open. How can I need to switch between the tabs. Fantastic, thank you very much. So this is our website. We launched last week our platform, a way to build end-to-end zero-knowledge applications. And there are a few things that you might find interesting here. So there's a speed test that you can run from your device, any device, your cell phone, your browser, at your laptop, and it tells you how many constraints, how many gates your device can process per second. And here, down here, it says how many Poseidon hashes you can process. It translates to a number of Poseidon hashes. I'll say more about that in a minute, but feel free to speed test your device. And the more interesting, I mean, what I wanted to show you is our marketplace. So basically, we launched a marketplace for people to enter and actually design their own apps, end-to-end apps, very, very easily, right? So I mean, if you go to, can you see what I'm doing? Great. So if you go to the marketplace, you can see, I mean, we have some projects here, for instance, proving a Fibonacci number. You have the inputs, you can define whether they're private, public, and then you hit prove. And that's how it works. But you can go to my projects, and you can define a new project. All you need to do is plug in your code. Right now, it supports C++ and Rust, and hit compile and prove, and it's going to work the way you see. So it's very simple, very intuitive for you to build a zero-knowledge app. Please enter. Play with it. We'll be happy to hear your feedback. Okay, so this is what I wanted to show you, and I want to go back to my... is it working? Fantastic. Okay, great. Thank you very much. So now let me tell you, what do we mean by usable privacy? Okay, so this is our vision. First of all, we want the tools to support standard toolchain, meaning that we don't want to introduce new languages, new libraries, because we want engineers, coders to feel comfortable. We don't want them to learn a new tool in order to code and build zero-knowledge apps, okay? So basically, we're aiming to what is called ZKVM. Affordable hardware. Nothing is more affordable than running this on your device. Portable implementation, right? Not just run it on any device. As I was saying, it could run from your cell phone, it can run from Blueberry Pi, anything. And the default should be privacy. So right now, many of the systems out there, the default is not privacy because they don't need privacy, right? Most of the off-chain applications, you basically aggregate many transactions, you need to process them, and then you need to provide a proof that you process them correctly. You don't need privacy there, so therefore privacy is not the default. They can become private, it's not a big problem, but the default, I mean, our goal is that the default will be zero knowledge. Okay, so today privacy comes with many trade-offs, unfortunately. For instance, if you want to support compliance, So you have to sometimes give up privacy because these tools are not always regulatory compliant. Privacy versus cost, right? It could be very, very costly to deploy current systems. You might need huge multi-core machines or buy many high computational power on Amazon machines, simulate many nodes, huge hardware. This could be very, very costly. What about usability, okay? As I was saying, currently there are specialized tools like Circum and other languages that are built toward integrating these tools. So if someone wants to design or build its own zero-knowledge app, it actually needs to learn a new language. It needs to know, to understand, to go into Circum's library and understand how to speak in that language, how to design a circuit in Circum's language that translated into a set of R1CS constraints. And finally, privacy versus trust. If I cannot support privacy, then I need to interact or have some intermediate party that holds my data, which I trust to keep it private. Okay, and as it stands, as I was saying, that zero-knowledge snarks fall short with the following. They require huge memory. That's why none of the current systems can actually run from a browser. They therefore don't support client-side proving yet. And I'm saying yet because it's the next thing. People are talking about it. People are trying to develop. Last week, some of my colleagues attended Denver, and there people actually gave a talk explaining their vision also about client-side proving. So we're not the only one that actually trying to do it. Okay, as I was saying, most ZK proofs are built for verifiability only. They're not supporting privacy or zero knowledge. It's not a big step, but they're not supporting it right now. And finally, they only offer privacy for specialized tools. Good. So let me explain a little bit about the ZK technology or the ZK behind our tech. And this goes back to the MPC and the head paradigm, the beautiful groundbreaking concept by Ishai et al. From 2007. And this paradigm provides a new look about the relationship between zero knowledge and MPC. We know that zero knowledge is a special case of MPC or 2PC. We know that if we have 2PC, we have zero knowledge because 2PC implies zero knowledge. But actually what they showed in this paper, a different way to construct zero knowledge from MPC that is black box. Let me say a little bit more about it. I just want to say that this paradigm has turned to have great potential, both in theory and in practice. And those constructions are hash-based systems, so they are considered to be post-quantum secure. And ever since, I think it was 2017, 2018, with Picnic, which was the first candidate for post-quantum signatures. It actually made it to the one of the 5 finalists in the NIST competition. And I really didn't list the entire list. There are many, many papers, including, I think, even 3 papers in recent AsiaCrypt, improving on post-quantum signatures based on the MPC and the head technique, all kind of assumptions, all kind of optimizations, all kind of abstractions, and MPC instantiations. So the great potential comes from the fact that it has a lot of flexibility in how you instantiate this paradigm. What will be the underlying building block or MPC you're using? Okay, so what do I mean by black box? And up until the IISc paper, pretty much all zero-knowledge constructions that we had for all NP relations worked by using a carp reduction, right? You basically needed to prove your system on an NP-complete problem. What IISc has shown is how to avoid using carp reductions, which is also, yeah, you don't need to have a carp reduction. You can prove it directly, and be black box in their relation, okay, in the NP relation. This is part of the contribution. And how do they do that? So let's assume, and I'll just give you the intuition. Let's assume I have an MPC protocol, okay, with some features. So they first defined a new functionality, right? MPC. We need to specify the functionality that the MPC computes. So, do I have a pointer? I don't know. So good. So look at this functionality. So R is the original NP functionality that we want to compute. I don't know if it works. Okay, and G is the MPC functionality where the witness is secret shared among the parties. So now, wait, am I going? Okay, good. So now here's how it works. Like this is the very basic construction on which we build on. So you have two parties, a prover and a verifier, and this is the functionality that they want to compute. And now the prover takes this MPC and think of it as a virtual protocol. That's why they call it in the head, because everything's going on is in the prover's head, right? The prover is going to secret share the witness into the parties. And now the parties are going to virtually interact with each other, creating a set of views, right? A protocol implies views. And those views are going to be committed to sent to the verifier as the first message, okay? Now this MPC, I only need a very, very, very basic requirement for this MPC, a semi-honest protocol with some very, very mild notion of privacy, you'll see. And now the verifier is going to challenge the prover because the verifier wants to make sure that the prover emulated this NP relation correctly. So it's going to send a random pair of parties for which the prover is going to reveal, and the verifier is going to check that these two views are consistent, right? Incoming message here are consistent with outgoing message here and vice versa, and that the parties' output is 1, because we want the NP relation to be satisfied. So it's a very simple way to explain. Think, this is like, this concept is amazing, right? You take an MPC and you get a zero knowledge. And if you hear one of the authors explain how they reach out to they came with this, they said that they sat down and thought, we have a computation, right? This computation, I mean, so far we used it we invested this computation in carbon reduction, right? This is where that was the heavy part. We want to come up with an alternative way to model this computation, and that's how they came up with this idea. Okay, so very briefly, yeah, and I'm skipping many details, but right, zero knowledge, we have to prove 3 properties. So at the high level, completeness is obtained by the correctness of the underlying MPC protocol. Zero knowledge is implied by privacy. So if your MPC protocol is secure against 2 corruptions, this is enough, right? The verifier sees 2 corruption, as is corrupting 2 parties, you get zero knowledge. And soundness is implied by, so they had some local to global consistency argument. If you basically check all pairs of views in the protocol, that implies a global consistency, and that will give you soundness. Then it means that the prover cannot cheat. It knows the witness. The protocol is from the security of the protocol. Good. Okay. What about communication complexity, or the proof length, right? So this is implied by the size sizes of the views of the protocol, right? The MPC, the virtual MPC protocol we're using. And in the original IISc paper, as well as a couple of follow-ups, the instantiations that were used implied linear size proof, meaning that the views were aligned or grew linearly with the size of the computation. And our goal is to, we wanted to see whether we could push, right, beyond linear proof size. And that was what came, or this is what behind the Ligero proof system, a paper from 2017 that actually started this journey, this process of developing zero-knowledge systems. And in this paper, we used an optimized version of an MPC protocol by Ivan and Yuval, DI06. It's not that in the original IISc this was not mentioned, this instantiation. We just used it in a different way. I'll show you how. And we had to extend the analysis in IISc. I'll also show you why. I just want to say that the way we used this, it was so inherently parallelizable, this proof, which is a huge, huge benefit if you want to use more hardware or use more cores. It's very, very simple or very easy to parallelize this because basically we're using Reed-Solomon codes. And the original construction in IISc had a linear time verifier, okay? And one way to make the verifier sublinear is to switch to a multi-instance setting where we want to prove multiple instances. There is a way to remove one of the checks in the protocol and make it sublinear. Okay, let me quickly tell you how do we actually build a Ligero proof. So we have a circuit. It could be Boolean, it could be arithmetic, and this is my circuit, my NP relation. And now I'm taking all the intermediate values. This is what we call an extended witness. This is how basically all zero-knowledge proof works, with an extended witness. In our case, we rearrange these values in a matrix with some repetitions, okay? It's between 2 to 3 repetitions. So the constants are very, very small. So now I have this matrix. I'll tell you how we do that. And then in the protocol itself, what you first do, you encode every row in the matrix, okay? You encode it using what we call packed secret sharing. I think we heard this in this workshop. It's a generalization of Shamir secret sharing, but you can actually, your secret is a vector. It's not just a single element. So now I encoded each row separately. And this is what the prover is kind of doing in its head. And in the protocol itself, we're first committing to this. So each column, think of it as a leaf of the Merkle tree. And this is where we use crypto, okay? We use hashes. And this root is sent to the verifier. And now, there are 2 phases in the protocol. In the first phase, the verifier is sending what we call multipliers, okay? And these multipliers are basically, think of them as the prover now, it's like a vector times matrix multiplication. So the prover is taking the linear combination of the rows in the encoded matrix and send them to the verifier. I'm ignoring zero knowledge for now, just to make it everything simpler, okay? So far, I'm not talking about privacy. And then in the second phase, the verifier is challenging the prover to open a subset of these columns to be checked consistently with the row that was sent in this third message. So I mean, this is at the high level what's happening in Ligero. Of course, I didn't tell you many things. What exactly are we checking in this phrase where we send this row? And we're checking several things. We're checking that this is a valid code word. We're checking that the constraints of the circuit are satisfied with respect to the matrix, both linear and quadratic constraint. And also, we have to check that the wiring is done correctly. So we have 3 tests. I didn't describe them here, but it's super simple to understand, at least the high level. And this is part of what's good in Ligero. It's very simple to explain. Okay, so what's the proof length here? So look, we need to send 1 row and multiple columns, right? But if you, if you fix the parameters of the matrix to minimize this this complexity, you will get a complexity of order square root circuit size. So we are working on square root chunks. And that's already an improvement and another benefit of Ligero, because most, for instance, if you look at Starkware, which is another hash-based zero knowledge, again, beautiful technology. They also use error-correcting codes, Reed-Solomon codes, and so on, but they have to work on much bigger chunks. Basically, their chunk or their polynomial is as large as the circuit. Okay, if you want to see more details, the original paper was published in 2017. In 2022, we updated, actually we published an hybrid version with optimized implementations and extended the proof, so really to make it much easier for people to look at the paper. And that was already quite efficient, actually very efficient, and was competitive with many other proof system out there in terms of the prover's running time. The prover was very, very efficient, even if it wasn't really linear time. It was polylog because of FFTs. Okay, so that was Ligero. But now, what is the actual challenge when you want to build such proof systems? As I was saying at the beginning, people were people cared about the circuit representation, right? We switched from carp reduction to circuit representation. Now we have multiple ways to represent our computation. We have our 1CS constraints and other ways to do it. The second step, or the second in the evolution of zero knowledge in research, people try to optimize the prover's running time. And indeed, we have very, very efficient provers running times. But what is the cost of doing that? And that is the major bottleneck, because it depends on the amount of resources you need to use to make your prover efficient and very, very practical. And indeed, this is the main bottleneck, because if you want to build client-side zero-knowledge proof systems, you cannot use a huge amount, multi-core, terabytes of hardware machines, because the simple users, we will not be able to use that. So that was our next question in our journey, and trying to understand how to minimize the resources of the prover. And remember, we worked in the hash-based zero-knowledge domain, and at the time, that was a few years back, it's still the same common knowledge. Hash-based zero-knowledge imply very efficient prover, but the proofs are medium size. And if you go to stronger assumptions, elliptic curves, public key assumptions, you can reduce the size of the proof, mostly because the algebraic structure of the proof systems, kind of homomorphism. You can kind of compress what's going on there. But the running time of the prover will be much higher, orders of magnitudes, because these are public key elliptic curves, much more less efficient operations. And we wanted to ask, we asked ourselves whether we can come up with a system that is time and space preserving under minimal assumptions, also in the hash-based domain systems, because it was already known how to do that, or this question was already answered, at least in theory, when public keys were allowed to be used. And that was our next paper that we published, was TCC 2022. And we showed that the answer is yes, and that you can define, you can design. It was the same ballpark, MPC and the head proof systems, where the computation is T and the space is S. You start with the computation with these parameters, then the zero knowledge proof will stay in the same ballpark up to polylog factors. And we also showed that it is tight. We had the lower bound in the paper. Okay, so that's wonderful, but that was highly theoretical. What about concrete efficiency? Because this is really our goal. And now I want to introduce you with the system that we are implementing and working with, and we called it Ligatron, which is the next generation of Ligero. That was a paper published at IEEE last year. With our lead engineer in the company, who actually implemented all that. And he has done a wonderful work. So this system is the only memory-efficient hash-based zero knowledge that currently exists. It is zero knowledge by default. It is ZKVM. We use VASM to implement it. So you basically can take any code, right now, as I was saying, C++, Rust, plug it into a platform, and it will already use this system to translate it into a VASM code and Ligatron. And this is what I showed you before. You could just run it from a browser. It's scalable, it's portable. We used web GPUs to implement it. And the reason we wanted to use GPUs is because any device that has GPU in it can just scale with our system. Okay, so what's the secret ingredient of Ligatron? So first of all, as I was saying, it is a hash base. So symmetric key, crypto are very fast. The technicality in the proof, or the underlying structure, is what called code interleaving. So remember I showed you the matrix? So this is essentially a code interleaving. It's a set of multiple code words. And it enabled us, so there is this term called shredding, sharding. People are trying to take a big problem and make it or break it into smaller problems. And this sharding is typically done using recursive composition. You take one proof which has a very fast prover but longer proof, and you compose it with another proof system which has less efficient prover but much shorter proof. And the composition of these two schemes give you the parameters that you want. Pretty much most proof systems out there that are implemented are using this recursion. We were able to avoid that using the internal structure of Ligatron. In particular, this matrix, if you can imagine that, the proof that I showed you before, you don't really need to store everything at memory like at the same time. You can actually reconstruct it while you run the computation. So for every test, remember I told you we have 3 tests, for every test, you just reconstruct the matrix from scratch. And that's why it's memory efficient. you don't really need to store everything in memory. So you just work on the fly. But there is no secret ingredient. So everything you see here is basically the properties we inherit from Ligero and MPC in the head. So that's what makes it so so nice, so easy to deploy, and also memory efficient and parallelizable. Okay, so let me give you some numbers and tell you what we've been doing so far. We try to compare ourselves to other two tools out there that trying to kind of aim to achieve, at least IISc, trying to achieve client-side proving. So first of all, Circum. Circum is a domain language tool that people use to take a circuit and translate it into a set of constraints. Beautiful work. Many people are using it. They put a lot of effort in that. But that cannot be used for client-side proving. I mean, we say prover key, we actually mean they use Groth 16. It's a huge CRS that needs to be kept in memory. You can't really use it for our purposes. IISc, they also declared, I mean, this is their goal. They're after client-side proving. And we try to benchmark their system. Again, take it with a pinch of salt. This is just our attempt to estimate the efficiency and complexity of their system. So we ran their system on M1 machine. And so what you see here, let's say around 50, when I say kilohertz, I mean 50,000 constraint, or sorry, so you can see down there, here. I don't have the, okay, here. So this is a measure of how many constraints you can process per second, okay? So this is Noir of IISc. And comparing to where we are currently with Ligero, so if you can see, if we run it on the same M1 machine, we can process between 250K to 1 million constraints on the same machine. And this range is whether if you go from one instance to multi-instances, right? Remember I told you for multi-instances you can go even faster. And if you try to run it on an M4 machine, which is a faster Mac machine, you can get even better or much higher number of constraints that can be processed. So that's, and this is actually is translated into 27,000 Poseidon hashes. Okay, for some reason I think this it skipped one slide. Okay. Okay, I still have time. I think when we switched between one of the slides was actually missed. But what I want to tell you is that so here's another citation by Vitalik. And so the reason we're looking at Poseidon hashes from the first place, first of all, so this is an MPC-friendly hashing. Currently, people are mostly using Kchuck, not just to implement the zero-knowledge proofs, as I was saying, the Merkle trees and so on. Also on Ethereum, right? They need to store all what do you want to say? I forgot the word. All the okay. When people want to transfer money, the transactions. Thank you. Yeah. Sorry, forgot the word. So they need to store all the transactions. So they need to verify that everything was done correctly. They use hashing. It's a huge data structure, and that's why Vitalik is actually encouraging people to work on and understand the security of Poseidon, because they're actually thinking of integrating Poseidon in Ethereum. And this is why everyone are benchmarking with respect to Poseidon. How many Poseidon hashes I can prove per second? This is like the common benchmark that you will see on everyone's slides. And this is actually what I wanted to show you, but maybe I'll get back to it. So, sorry, let me, maybe I can try to go back, because I kind of skipped it. Yes. So this is what I wanted to show you, and it was skipped. So this is a table taken from Starkware's presentation. They introduced it last summer. And so they had two versions of their systems, Stone and Stew. And look, the first one, Stone, the first column, they implemented their system on 252 bits field. And their benchmark was they managed to come up to process around 500 hashes per second. When they introduced Stew, they switched to a smaller field size, like 31 bits. And they made a huge improvement, 1000x. But their, I mean, if you can see down there, their implementation is run on a 4-core machine. Right? This is what they reported. And now I want to show you to compare with what we do, where we are currently at Ligero. First of all, this is from a browser, so no multi-core machine. And we stick with a large field size, and this is because our goal is to, I mean, we are after client-side proving, especially identity-based applications. And these are mostly aligned with signature schemes, like ECDSA and so on, that work on larger fields. So that's why we're still at a large field, but we will have also an implementation for a smaller field. And a look at the range right now. So this is this 20,000, as I was told you before, an M4 machine. And surely if we'll switch to a smaller field, we'll get easily a 10x improvement. But what I want to tell you is that we are far away, about 20x far away from proving an Ethereum block real time. So we're not that far from actually getting what Vitalik wants. Okay, so let me conclude. Now I can go back to the concluding slides. Yes, I'm here. Good. So, today our end-to-end platform supports C++, Rust. Very, very soon to come, we are integrating Circum. So I told you Circum had done wonderful work. We want the platform to enjoy the benefits of Circum as well. So we are integrating that. Our goal is to come up with a plug-and-play identity gadget. So essentially, no code, zero knowledge. We're not there yet. But the goal is to have users to, right? I mean, Europe is switching to digital identity and so on. We want people to have, be able to go into an app, define how they want to prove their credentials, and then use this gadget, plug in this gadget in their app, in their browser, wherever they want. Okay? So this is what we call a no-code, zero knowledge. So this is hopefully coming soon. And for ZK Validiums, which is what the applications that are used for organizations, for companies that want to run off-chain, We would like to, our goal is to come up with ZK validiums, lightweight ZK validiums you can actually run and have limitless ability to compute off-chain. The longer terms, on the future goals is to cross-link other languages, again, everything is wonderful. People have put a lot of effort. We would like to have the ability that people can install API and plug into other languages, they can work with circuits with different representations. So this is definitely in the pipeline. I told you Ethereum block proving. This is one of the benchmarks we want to achieve. And to be able to prove arbitrary AI computations, inferences, and so on, for when the model is private. So stay tuned, and I'm almost done. Please test our system. We'll be happy to hear your feedback. Test the speed. If you're running it from Safari, you need to enable a web GPU for it to run. And talk to us. Show us your speed. We're really anxious and curious to hear how it works. And finally, this is our motto, right? We want to build anywhere, we want to build with any language, and we want to build everywhere. So this is essentially the goal, right? ZK, anywhere, everywhere. Thank you.
Thank you, Carmen, for an excellent talk. Do we have questions from the audience? I suspect we do.
Yeah, I'm not sure this is a very precise question at all, but I was wondering about the conceptual relationship between MPC in the head and Ligero. It sounded, from what you were saying, as if the thinking behind Ligero was inspired from MPC in the head. But when you talked about Ligero, you went from the circuit-based representation. On the face of it, it didn't seem as if there was any MPC there. But
I thought you would see it. It's your protocol. No, it's an honest majority protocol. Think of a protocol where you, the circuit that the MPC wants to compute is very low, like depth 3. And basically, each party is secret share its own input using packed secret sharing. Okay, and the input is large, is the circuit. So, and each column is a view of a party.
Thank you. I see some more hands.
Thank you so much for the great talk. I saw that you talked about the MPC in the head giving us soundness by this global to local to global consistency. But in a lot of applications, what we really care about is knowledge soundness, because everything that we are trying to prove is succinct, so soundness doesn't really help. So is there a...
No, wait, I didn't understand. What do you mean soundness didn't really help? Soundness is something that you must.
So for example, if I want to prove that I know a discrete log, that's a true statement. Soundness doesn't really help. What we care about is
you need
knowledge.
a stronger. That's what you mean. You need a stronger.
Right,
Yes,
so
you can show that it's also a proof of knowledge.
Oh, okay, thanks.
Hello.
Where?
Here.
Oh, yes.
So have you done any comparison with the new ultra-honk backend of Noir, or there's a Plonk backend of Circum as well? So those are more efficient about the constraints.
So I don't remember. So we prepared these comparisons for eDenver. So we were a couple of weeks back. So if they publish something since then, might not be updated. But as I was saying, take it with a pinch of salt. But this is kind of more of a ballpark of where we are.
I see. And what circuit did you use for evaluating these results? Like, what ZK circuit did you actually use for
The Poseidon hashes.
Poseidon hashes,
Yes.
okay. And you said that there's like future work that you're considering for linking the ZK languages. So can you talk about like how you exactly plan to do that, or like, what is the idea there?
Well, yes and no. I mean, no. I know what is the vision, right? I don't know how. I can tell you the engineering work behind it. The goal is to have an API that you can actually call to each of these. So you might be able to right in the platform that I showed you, you can plug in, you can use a description circuit that is written as using Circum, and then compile it into a zero-knowledge proof. Same with Noir and so again, the goal is to have generality in that sense. I don't know if I'm answering your question, but come talk to me afterward. I'll say more.
Thank you.
Hello. Here. Yeah.
Ha.
Sorry.
Hi.
Yeah, great talk.
Thank you.
So what I am slightly confused about talking about verifier time. So if you compare with the snots, I think you have a slide there, but no like concrete comparison. So I mean, what is the cost we are paying for this improvement in the prover side?
So when you talk about client-side proving, right? You are the prover. The client is the prover. And you, mainly the bottleneck was how to call the prover from your computer, right? So far, we didn't know how to do it. Because if you use Starkware, if you use other proof systems, you really needed much more powerful machines to do that. So let's assume you want to prove something about your credentials. Ligatron is the only system you could do that for.
So I mean, in terms of like, is there a trade-off in terms of like?
In terms of resources, memory that you need to use.
In terms of the verification side, like let's say the proof will be verification on chain, right? So in that sense, like.
Yeah. I'm not talking about on chain, right? That's a different question. Yes, I'm talking about. Yeah. I'm talking about right now how to log in, enter a password, and now proving something that you're eligible to. Yes.
Okay. Thanks. Yeah.
Thank you, everyone. Far be it from me to keep cryptographers from their coffee. I think, unfortunately, for time reasons, we will have.
Okay, come and ask me. Come and ask me offline. I'll be happy to answer. Thank you very much.
Thank you. Please join me in thanking Carmit again. That concludes this session.
Oh.
As soon as we do a quick photo op. And I believe we will have a short coffee break now and returning at 11:40. Can I get maybe a nod from one of the organizers if I'm correct? Okay, 11:40. Thank you all very much.
Okay. It's fine. Yeah. Sounds good. Thanks.
Shall we start? Welcome back from the coffee break, everyone. So for this session, we have with us the first talk by Sridhar, who's a PhD candidate at UC Berkeley, and he will talk about Instapoker, real-time on-chain poker. The floor is yours.
Thanks for the introduction. So yeah, I'll be talking about Instapoker. This is joint work with Sanjam, Aniket, Pratya, and Rohit. So, well, this talks about a very common problem that most of us face in the morning when we wake up. We want to play poker. So, how do you do this, given that we don't potentially have access to casinos near us? We log on to our favorite website, or perhaps now we're in the age of Web3, perhaps we have funds on a cryptocurrency somewhere. So we log on to your favorite blockchain, and then, what's the experience you want to have? You want to have something that simulates what a real poker game is like. You have a dealer who comes, shuffles a deck, gives it to you, and then you want to start playing. But, it works fine in person where you can see the dealer shuffling the deck in front of you, and they're, giving commission boards and so on. But what happens if you're online where you don't know who's actually giving the service, who's providing the service to you? And perhaps the dealer is malicious, perhaps they're collaborating with one of the parties, and perhaps the shuffle deck that I give to you is not even a permutation. It's just in order, let's say. Or it's all aces even. What's the guarantee that it's actually even a deck, right? And this is actually an issue in practice. It turns out there are a bunch of large-scale cheating scandals that have been happening, and there needs to be solutions to this. So given the workshop we're at, what is the solution we expect? It's MPC, as expected. So this is a solution that's been known for a while. It's a turn-by-turn based solution that people have worked on, and it's also been implemented by some companies. So what's the idea here? The idea is the players, when they join the table, say some player starts with a bunch of encrypted cards, and they pass it along, and every single player is going to permute the cards and prove that they permuted it correctly, and then pass it along. And as long as one party is honest, the final output is guaranteed to be random, a random permutation. And that's great because it's the least amount of assumptions you can make in terms of honesty, because as long as you're one honest party and you follow the protocol, you're good. But it's not great for user experience in the sense that the users are doing all the work that they don't want to do potentially, and there's high latency. There's as many rounds as the number of players. The players do a lot of work. They need to produce proofs of correct encryption, proof of correct shuffling rather, and pass it along and wait for a while. And what happens when a player leaves? If a player just drops out in the middle, you're going to have some problems because you just need to start the protocol all over again. So, well, is there some way to improve this and perhaps improve player experience, which is sort of the goal of, I guess, a high-level goal of this work? How do you make the players do less work while still getting good guarantees? So one thing we can look at is, a shuffle deck has nothing to do with the players. The players don't need to exist for you to shuffle the deck. So can you do it offline? Is shuffling an inputless functionality? It kind of is. Notice that we need to finally produce a private permutation. You can't there's not a public permutation that you produce at the end of it because you can't just deal all the cards face up. That doesn't help you. So it's sort of an inputless functionality in the sense that as long as you know the players' identities, you can produce encryptions to them. But if you don't know what the players' public keys are, then it's not really inputless. So for now, let's assume that players register ahead of time and the players are known, which is not really true, assuming that you want to do these things in the pre-processing phase. But I'll remove this assumption later, close to the end of the talk. But for now, let's assume that this is an inputless functionality and the players' identities are somehow known. So say the public keys are known in the pre-processing phase. So in this case, perhaps there are a bunch of parties that decided to provide the MPC service that provide a service to generate permutations. They can come along, generate a bunch of permuted encrypted decks, put them on the blockchain, and then leave. So in some sense, all they're doing is they're being ephemeral. They just produce a bunch of proofs. They don't need to talk anymore. They just encrypt the cards and go away. So of course, you need some proof that it is actually a permutation. You can't get away from that. And latency goes down for the players. It's a better experience for the players overall because all they're doing is coming to the game, downloading whatever encrypted deck they want, decrypting the cards, and they start playing. So that's sort of the, I guess, offline model that you can have because you can generate all these permutations offline. And you have this sort of on-chain deck buffer of sorts where these offline parties just, after they compute this permuted encrypted deck, they can submit it onto the chain. And the players, when they arrive, they can just pull their own game ID-based deck and then start playing. So this is good for the players. The players don't do a lot of work. Not much latency because all this is done offline. And this trust assumption, I guess now you need to rely that at least, say, one party out of all these parties is honest, which wasn't true in the previous case where all you had to assume that you yourself are honest as a player. And robustness is not something I'll talk about too much here, but any aborts in the offline phase don't really affect your game experience too much because you can just run the protocol again until you succeed. And as long as there are enough permitted decks in the buffer, you should be good. And in some sense, because the functionality is inputless, you can, if there's an abort, you can just ask all parties to open the random coins. And in some sense, that gives you some notion of identifiability of potentially who's been cheating, if there's some cheater. So given that sort of model that we're in, what happens in the offline and online phase? So in the offline phase, the MPC service generates generates a permutation, and generates the encryptions to these cards, and generates a proof of correctness for each of these encryptions. And the players join the table, get the deck, verify a proof. Potentially the proof is verified by a smart contract or something else on chain, and then they just decrypt the cards and start playing. So let's look at each of these steps one by one for the offline phase. What am I doing on time? Okay. So, of course, there are lots of ways to generate a permutation inside an MPC. This is one of the ways. So, some constraints that we have here are, well, we are only working over a small range. We only need permutations of, let's say, 1 to 52 if you want a single deck. If you want multiple decks, maybe it's 1 to 104, and so on. And for reasons that will be later clear, we also need these to be secret shared over a large prime field, in particularly exponentially large in a security parameter. This is because eventually we will be using this in conjunction with a proof generation inside the MPC as well, which requires large fields for soundness. So, well, so step one is how do you generate, let's say, a random small element inside an MPC? Let's start with an even simpler case, a small warm-up of how do you generate a small shared random bit. This is something we've seen even earlier in this workshop. It's a classical protocol. To generate a random bit, or let's say -1, 1, you can sample a random sharing, compute a square, reconstruct, and then basically compute a canonical square root and then cancel it out with x. And you get a sharing of +or -1. This works as long as p is odd, which in our case is odd because p is a prime. And this can be extended to give you a random small shared element in a slightly larger range. One way to do this is on the left side. You can generate a bunch of random shared bits, and then you can linearly combine them to get a sharing inside a space that's a power of 2. And this works for most of the prime fields that we care about for proof systems because most of them are highly two-adic. So it works out fine. There's also this other generalization you can have where you can directly get any output range you want. But of course, it requires your prime to be 1 mod n, and you need to have n roots of unity. And this is not true for, I mean, if you're allowed to choose what prime field you want your sharings to be over, this works fine. But if not, it doesn't. So we can just stick with the one on the left. But of course, notice that what we want is a permutation of size 52, not, say, 64 or some power of 2. And we eventually will get rid of some duplicates or get rid of the unwanted quads in some sense. So one way to generate a permutation given a way to generate a random number is generate a large number of random numbers. With high probability, you will have at least one of each element. And then you can discard the duplicates. And that gives you a permutation. The question is, how do you discard these duplicates inside the MPC? The naive way of checking for equality between every pair of elements is not ideal because it's quadratic. But we can, since we are OK with using cryptography, we will use a lot eventually. One thing we can do is use a distributed PRF inside the MPC. And we use the .SC impulse key PRF, which works with secret shared inputs as well as secret shared secret key. And now we can reconstruct these PRFs inside. And this tells us which of these inputs are actually equal, and then we discard them. So this gives us a permutation. And there are, of course, other ways to do this. You can replace this part of the protocol with your favorite protocol to generate a permutation. And now you need to generate encryptions. Now notice that, of course, we have only sharings of these cards. And we need to generate encryptions which have to be reconstructed without. So any linearly homomorphic encryption will work. And let's say we start with Algoma. This version of it doesn't work simply because it's multiplicatively homomorphic and not additively. So we can modify this to an exponential version where the message is in the exponent. And now this is additively homomorphic. But of course, the problem is the decryption is now going to give you g to the m and not m. And this is not great in general because you cannot recover a message from the exponent because of discrete log is hard. But in our case, this is fine because our messages are all just cards, which is just, say, 1 to 52. There are at most 52 possibilities. So you can just brute force decrypt or even have a lookup table at best. So we also have this multi-receiver version, which we will need eventually because we need to encrypt cards to a bunch of parties, as many as there are on the table. And there's a small optimization here, which is we use the same first element of the ciphertext, G to the R, for all the encryptions. And this optimization not only saves space, but is also sort of crucial for a proof system that we'll need later. So now that we have an encryption, or how to generate encryption for the cards, now how do you generate a proof of correctness for these encryptions? By proof of correctness, I mean that how do you actually prove that these encryptions form a permutation? So I'll sort of detail what I need from this primitive, and why I call it encrypt and prove will be clear in the next slide. But I've defined this thing called an SVME, which is, say, succinctly verifiable multi-receiver encryption. And what do I need? I need to encrypt messages to multiple public keys, which I've done. And I need to prove some relation on the underlying plain text. In our case, it's a permutation relation, but as a generalized primitive, this should be able to prove any efficiently checkable relation. And the succinctness is useful because this will eventually go on chain. So I want the proof size to be ideally constant, independent of the relation, and the number of ciphertexts. So why am I calling this encrypt and proof? So this, in some sense, is a slight extension of the notion of commit and prove systems. So a commit and proof system, or a commit and proof snark, is a protocol between a prover and a verifier, where there exists a commitment to some witness, and the prover convinces the verifier that the committed witness satisfies some relation. And I guess the encrypt and prove version of it is just a slight extension where you have an encryption, and you do prove basically the same thing. And one sort of generic way to build this from any commit and prove snark is just have a wrapper around it and prove that the encryption and commitment are somehow linked. So the main question is, how do you design this linking proof? So at a very high level, this is what it looks like. So you have a vector commitment to a bunch of values. You have a bunch of encryptions. Those IDs should be public keys. That's a spoiler for later. So, I mean, if you just have two polynomial commitments, how do you prove that they're equal? We use what 50% of cryptography uses. We use what's-zip lemma. And two polynomials are equal if they evaluate the same value at a random point. We can evaluate the polynomial commitment at a random point. But how do you evaluate your encryptions? Because you have a lot of encryptions, all to different identities, different public keys. And how do you evaluate these as a polynomial at some point? So one thing you can notice is these essentially form a non-succinct polynomial commitment. And evaluating this essentially looks like batching. You can batch these with different powers of your evaluation point in the exponent, and it works out fine. Of course, there are two elements of the ciphertext. There are other issues we need to sort out and make sure everything works fine. And there are some additional checks you need to do to show that your encryptions are well formed. So all these are possible to do. But recall that we need to do all of these inside the MPC, because our initial witness is secret shared. Our initial witnesses are just the cards that have been secret shared. And it turns out that, well, commit and prove snarks have been shown to be, or at least the specific protocol has been shown to be distributable, or can be performed inside an MPC. This is the work of collaborative snarks by Alex and Dan Bonnet. And we can extend this to encrypt and proof by essentially using a recipe from before where we have a wrapper, the collaborative snark, and we specifically just need the permutation proof part of it. And since the homomorphic encryption, the encryption is linearly homomorphic, we can also use that inside the MPC. And the proof system that I just showed here is also carefully made, so it can also be completely done inside the MPC. So given this, we now have a recipe for what the offline phase does. So the offline phase does these three things. So generates the permuted card text, generates encryptions, and the proof of correctness. And now their work is done. This committee that generated these encryptions proofs can just submit them to the blockchain, perhaps obtain some financial incentive for doing so, just obtain some reward, and then they just leave. They don't need to be present for any part of the protocol later. Now the player's work is easy. But I made an assumption that was not very ideal at some point, right? So I made the assumption that the player's identities are known ahead of time. this is not ideal because players don't decide one day or 1 week ago that they want to play 1 week in the future. So what do you do when the player's identities or the public key is not known at the time of shuffling? What do you encrypt the cards to? You need to encrypt the cards to some identity that the players can decrypt in the future, right? So one way to do this is you can have, say, a bunch of other parties that keep running, let's say these parties that I call keepers, that keep running, say, DKGs for every single player in every single game, right? They run a new distributed key generation protocol, and let's say sample a new public and private key pair for each player in a threshold fashion. And they pass this over to the shufflers, who are then going to encrypt these cards to these new public keys that have been generated. And when the players arrive, these parties can just give them the decryption keys to those new public key identities that they made. This works fine, but the issue is you need to run a new distributed key generation protocol for every single player and every single game and every single seat, which is not ideal. You don't want to run that many, and this doesn't scale very well. So one natural way to solve this is this concept of identity-based encryption, which is sort of the spoiler that I had IDs before I forgot to change the slide. So the constraints are basically that you cannot use the player's public keys because you don't know who the players are. The players don't exist yet. And this must be distributable, so we need the same linearly homomorphic property as before. And the Bonnet-Franklin IB is a very similar form of encryption scheme to the El-Gamal encryption. It has the same kind of basic structure. It's just that it uses pairings. And this can also be made linearly homomorphic in the same way, where you can put the message in the exponent. And this is, again, it's fine because it's only a small range. So the final model looks basically like this. So you have IB encrypted DEX and proofs that the shufflers generate. And these shufflers can now, these IDs can simply be something like, OK, here's the game ID and here's the seat. And when the players join, all they can do is they just need to send a request saying, I'm playing game number 21, I'm in seat number 5, give me my decryption key. And then the keepers can submit the decryption keys. So this division into two sets of parties is sort of required. So the shuffling parties that do most of the MPC work can sort of be ephemeral. They can just come and go when they want to. Come, generate proofs, and then leave. While these keepers are like a smaller set of parties that potentially stay and then offer the, decryption keys encrypted to the players whenever they join the table. So the keepers sort of provide the liveness and the real-time notion for the game, while the shufflers do the offline phase and just generate a bunch of things. So these are some experiments that we run. These are somewhat fairly unoptimized code. And even though I've said 64 cards, what we want is finally something of size 52 cards, right? We want a deck of cards and not a permutation of size 64. So how do you discard these extra things? One thing you can do is at some point in the past, I said, OK, you're going to compute these PRFs inside your MPC. And what you can do is you can also compute PRFs explicitly on the cards from 53 to 64, and then discard those as well. So that sort of reduces your permutation from the size 64 to 52. And with that, I'll conclude. Thanks.
Thank you very much for the talk. Do we have any questions?
Hi, thanks for the great talk.
OK.
So for the shuffling technique, how does it compare to like mixing style circuits like Honey Badger MPC?
Yeah, so things like mix nets and those kinds of things we did consider them at the start. But I think at some point the issue was that we would have to sample a new mix net essentially for each shuffle. And sampling at each shuffle is not ideal because it doesn't scale very well.
Okay.
And you need to sample a matrix essentially for that.
Hi, sorry, in the last slide, what is the unit, millisecond, second?
Oh, sorry, my bad, it's seconds.
Thanks.
So you have the encryption to be converted in this step to, this is unknown, and then you do not know who would come and start the play, so you have to convert that encryption into the person who is joining
Yeah, so
the game, right? Can't we use the proxy re-encryption technology for that? It's very well known that the ciphertext encrypted under one key can be converted into ciphertext to be encrypted in another key, independent of the message that is encrypted. The original message need not be known and all. And we have interesting techniques. So have you kind of thought about it, or?
no, I think that should be doable, but I feel like IB still has the advantage that, so in that case, you would still need to have some public key to encrypt to in the first place.
That is, you have some fixed number of guys around that keepers.
Yeah, but that's already happening.
That's already you have. So when a new guy comes in to join, whatever is encrypted under that guy's one can be converted into the encryption of the guy who is joining.
But this is strictly less work, because instead of converting an encryption, all you're doing is giving the decryption keys to the players.
Okay, if that doesn't affect the secrecy or something like that, that's okay. Here you don't have to give the key, number one, and number two, it's much simpler than the pairing-based solution.
Okay.
Much simpler protocols are available for proxy re-encryption.
Yeah, I'll discuss it offline.
Yes, yes, thank you.
Any more questions? Maybe a quick question from me. What is the maximum message space you can support that satisfies the IBE and the LGML?
Pretty much any message space should work. The only bottleneck is going to be the generating the permutation step. Everything else works as long as your message space is smaller than the field size. And the field size is typically fairly large.
Thank you. If there are no more questions, let's thank the speaker again. The second speaker of the session today is Pratik Soni, who is an assistant professor at the University of Utah, and he's going to talk about functional adapter signatures beyond all or nothing blockchain-based payments. The floor is yours.
Thank you. Thanks. Thank you for the introduction. I'm going to talk about functional adapter signatures, but what's more important is this idea of going beyond all or nothing blockchain style payments. So this is based on joint work with Nikhil Vanjani from CMU, Arvind from University of Sydney, and my student Garrett Grainer. So let's begin. We are at a TP-MPC, so clearly I have to motivate it from a MPC viewpoint. So what we are going to look at is this question of fair exchange. So it's a two-party computation between two people. Let's assume that they have some secret inputs, X and Y, and they publicly announce their commitments to their secret inputs. And what they would like to do is this very basic functionality of swapping or exchanging their inputs. In terms of security, what we want is fairness. And note that this is the dishonest majority setting because there are only two parties. One of them is going to be corrupt, which is what makes fairness challenging. In particular, fairness means that either both parties are happy or both are sad. Or in other words, they get their outputs or neither of them get the output. Of course, there is this implicit notion of authenticity in the sense that each party should get the real value behind the commitments, but I'm going to ignore authenticity for the rest of this talk because clearly the talk is about fairness. And while simple, fair exchange actually models a lot of interesting financial contracts. So for example, you could imagine this is even predating the blockchain mania, where you wanted to kind of buy certified software and people were conceiving this notion of payments, digital payments using signatures. So you can now imagine that if you want to buy a certified software, it's basically trying to exchange two signatures. And more recently, with kind of rise of different digital currencies, people are interested in swapping tokens from Ethereum to Bitcoin and so on and so forth. And what's going to be more relevant for today's talk is this broader question of sale of digital secrets. So you can imagine that a seller has some NP witness. In this case, one of my favorite examples is a solution to a Sudoku puzzle. And let's say there's a buyer who's willing to pay a Bitcoin for learning the solution. And I'm going to term this as a sale of a digital secret. So fair exchange, when you have a trusted third party, is actually very, very easy. Both parties can send their inputs, in this case, Bitcoin and the secret or the solution, and the trusted party kind of executes the contract and ensuring fairness, okay? In fact, while trusted party kind of makes this simple, people have started looking at removing or reducing the reliance on trusted party, and hence only kind of thinking about scenarios where you need the trusted party in a very pessimistic situation. So there are these optimalistically fair protocols that people are thinking about where they are reducing reliance on trusted parties. Unfortunately, completely getting rid of trust is impossible. And this actually goes back to this very nice work of Pagnia and Gartner in '99, where they showed that this idea of fair exchange kind of reduces to the classical FLP result in consensus and distributed systems. Having said that, there are some feasibility without kind of trusted parties, but these require timing assumptions, which are non-standard, so I'm going to ignore them for the rest of this talk. So clearly, we know how to do fair exchange when there is a trusted third party. While that is a good, it works very well in practice, it would be amazing to have a decentralized solution to kind of avoid the single point of failure. And in fact, the advent of blockchains has actually renewed attention in this problem space, where the idea is to kind of replace the third party with a blockchain. And clearly, more advanced blockchains like Ethereum, which support smart contracts, you can clearly deploy a smart contract on the N1 chain itself that can handle the trade by itself. However, these smart contracts turn to be very expensive. So recently, there's a beautiful kind of solution to this problem that says, if you want to do this fair sale of digital good, the amount of resources you need is actually just equivalent to doing a simple transfer. And the key idea here is to actually build these adapter signatures, which are extensions of digital signatures like Schnorr, and they execute kind of this reduction of sale to a simple payment by doing some off-chain computation. Okay? So what are these adapter signatures or adapters for digital signatures? So they extend digital signatures, and on top of that, they have additional algorithms that actually model a fair sale scenario. So in particular, there are two algorithms called pre-sign and adapt. These are supposed to be kind of modeling the signing algorithms. In particular, pre-sign is an algorithm that allows a buyer who wants to pay and has a signing key to generate a pre-signature to the actual signature. So you can imagine this to be like a locked version or an encrypted version or a partial signature. And the seller who has the solution or the NP witness can actually adapt it into a full signature. And then it can go on the blockchain and post this signature to get paid. And then there is this additional algorithm called extract, which allows the buyer to actually just look at the pre-signature and the signature and extract the solution, or rather the information that it was trying to learn. Now, if you notice, the pre-sign and adapt actually is nothing but a witness encryption of a signature. But what makes adaptive signatures very, very different is this additional algorithm called extract that allows the buyer to extract the solution from the encryption and the plain text. So that's what adaptive signatures are. And they've been increasingly kind of looked at as better alternatives to smart contracts because of multiple reasons. One of them, as I was mentioning, the fees that are associated with adapter signatures are just a simple payment transfer, no matter how complex is your NP statement or NP solution that you're trying to learn. It's compatible with legacy blockchains like Bitcoin, which do not support any smart contract functionalities. And what's great about adapter signatures in the last few years is that people are actually building them adapters for widely deployed signatures like Schnorr, BBS, Dilithium, ECDSA, so you can readily adopt them as part of existing systems. So what's the catch? The catch, which is kind of the main focus of our work, is that adapters, however great, only enable all or nothing style payments, in the sense that buyer either learns all of the seller's secret, in which case the seller gets paid, or nothing about it, in which case the seller doesn't get paid. Okay? And let's go back to the Sudoku example, where maybe the buyer is not interested in learning the whole solution or buying the whole solution. Maybe it's struggling only on one column or one row and only wants to kind of buy that particular or partial solution. That's actually the focus of our work, this idea of fair functional sale of digital information, wherein you can imagine there are two, again, entities, a buyer and a seller. Seller publicly announces a commitment to the secret or the witness that it's trying to sell. The buyer here has a Bitcoin and a function that it would like to learn from this, of the seller's input. And the two PC that they are executing is transfer the Bitcoin to the seller and only learn the function output on the seller's secret. Okay? So we need the same properties. The fairness comes in again. But on top of that, what we really need is privacy, in the sense that malicious buyer, they shouldn't be able to learn any other information beyond just the output that they are interested in. So for example, if you are only interested in one row of the Sudoku solution, clearly the buyer shouldn't learn the whole Sudoku solution in the process. And here are some motivating applications that we look at in our works. One is this idea of doing medical analytics, where you can imagine that the seller has a database of patients, and clearly by HIPAA compliance laws, it's not allowed to kind of reveal this database, but may be interested or incentivized to reveal some functional information that may help, like a research organization, to gather some statistics. So some examples of functions here that are popular are computing, let's say, a mean on statistics like mean, variance, covariance, and so on. The second motivating application is from the ML Mania, which is where maybe you want, the seller actually holds a high quality data set, and the buyer wants to maybe fine tune its model. And you can now basically model this as a functional fair exchange, where the functions are actually going to be like tuning an SGD classifier, image classification, or evaluating high degree polynomials of seller's input. So those are some motivating examples. I'm going to show you results on both of these fronts as we go later in the talk. So very, very kind of high level bird's eye view, our both works actually are trying to deliver on this question of executing functional fair exchange via this idea or an extension of adapter signatures called functional adapter signatures. In particular, we keep the fees equivalent to a simple transfer. We are still compatible with legacy blockchains. We can bank on deployment-ready construction, so you get all the nice properties about adapters, but you also introduce this notion of privacy, which we are able to achieve. So just a little bit more detail about the contributions, and I'm trying to divide this into theory and practice. I did this before I heard Karmit's talk, so this practical contribution is more on the implementation side rather than usability side, so pardon me for that. So at a conceptual level, what we do is we formalize the security of functional adapter signatures. We give a generic construction for linear functions that actually builds from functional encryption and adapter signatures. The moment I say this, I already see some people trying to question the efficiency because I'm talking about functional encryption, but hold on to that thought. I'm going to get to it later in the talk. On practice, we actually have several instantiations, one from prime order groups, also from lattices. We implement and evaluate it for large database analytics. In a subsequent work, which is actually under submission, we give a generic construction that goes beyond linear functions to all functions, but replace functional encryption with homomorphic encryption. And again, we instantiate this in multiple ways using different homomorphic encryption schemes like LHE, BGN, which is a degree 2 homomorphism, or Torus-based FHE, which is implemented in Zama's ML suite. And of course, we have an implementation for linear quadratic fine-tuning SGD classifier. So that's kind of at a very high level what our work does. In the rest of this talk, I want to just give you high-level ideas on why this problem is interesting, what are the challenges, and what do we end up achieving in the process. So let's start maybe by looking at the syntax of functional adapter signatures. For that, I just want to recall that the syntax of adapter signatures. So adapter signatures actually are an extension of digital signatures that we use, we love, we kind of work on it for a significant fraction of time. So digital signatures have 3 algorithms: keygen, sign, and verify. We also need like a hard relation, linear functions to higher degree polynomial evaluations, but also are able to kind of get better efficiency as compared to the FE approach. And this basically is the graph that helps you see that. So the red line is basically the prior work, and the blue line is the LHE work. As you can see, the blue line is actually significantly better than the red line. And the green line is actually the degree 2 HE based FAS that supports degree 2 functions, which is clearly significantly lower than the SNARK approach that I kind of mentioned in the warm-up. So with that, I'll just say that we also implemented this for fine-tuning SGD classifiers. Here are the numbers. We don't claim that they look super pretty, but this is an unoptimized implementation. The key point here is to note that what is the dominating cost is the homomorphic evaluation on the seller and the buyer side. But in order to kind of get this implementation working, we had to work around kind of Zama, play around with it to enable this randomness tracking for homomorphic evaluation, which required a lot of messy kind of code changes, but we are able to do that. We plan to continue optimizing this code in the future. Shameless plug, since we are concluding this workshop, I want to announce this another workshop that we are doing on fairness and distributed applications at FC, being organized by me, Chenda, Arvind, and Kerr. If you are interested in giving a talk, please feel free to kind of send us an email here. And with that, I'm going to pause my talk and take some questions. Thank you.
Thank you very much for the nice talk and for the invitation to the workshop. Are there any questions from the audience? Yeah.
Thanks for the nice talk. I got a sense from looking at your constructions that the seller always learns the function f in the clear.
Mm-hmm.
Do you envision a variant of this where you have some kind of privacy for the function itself, or does that not make sense?
So just to correct you, I think you said the seller learns the output in the clear. No, it's the function.
The function.
Yeah. So I think it's a very, very important question and goes back to this application of machine learning inference where maybe the buyer wants to keep the function private itself. We have thought about this question without strong progress to kind of claim, but clearly this would either require a function private functional encryption or a function private homomorphic encryption, which on top of that, they need to kind of satisfy this compatibility with Schnorr signature. So with all of that restrictions, it's unclear whether we would have a construction, but definitely that is a very, very important problem to think about. I didn't put it up on the slide, so you should consider that as the 4th bullet.
Thank you.
We have a minute if there is one more question. All right, then let's thank the speaker again.
Thanks.
And this session is concluded with a talk by, I hope I pronounce it correctly, Michael Adzeb. Yes, good, from Fireblocks. And he will talk about the best of both worlds, round optimized 2PC ECDSA at the cost of only 1 OLE with applications to embedded cryptocurrency wallets. The floor is yours.
Thanks for the introduction. So I'm Michael Adzeb. I'm senior cryptography engineer at Fireblocks. And today I will present you the result of my work with my co-authors, Kosti Blor, Geoffroy Couteau, Arik Garansky, Antoine Jou, and Nikos Makrianis, titled The Best of Both Worlds, Round Optimized 2PC CDSA at the cost of only 1 OLE. What will guide us through this journey is the following plan. First, I will start by a short introduction explaining our motivation to work on that topic. And then I will deep dive into the protocol itself. I will then explain some new techniques that we use to make our protocol more efficient and faster. And I will conclude by listing a few open questions and future work. Let's start by the introduction. So you have to know that trillions of dollars, with a T, were transferred on various blockchains. Most of the transactions are actually signed using ECDSA, and at Fireblocks, we secured more than $6 trillion already using our MPC ECDSA solution. So this makes blockchains a target of choice for a hacker. And for example, only a few weeks ago, there was an attack where more than $1.5 billion were stolen on Ethereum. Blockchains, in average, see millions of transactions per day. And so transactions need to be highly secure, fast, of course, and we need to avoid a single point of failure. So threshold ECDSA seems to be the way to go. What would be the ideal solutions for blockchain wallets? Of course, first we want something that has a low computational overhead, that only use low communication. The exchanged messages should be ideally small. We also want optimal round complexity because each round of communication between the parties induce latency. And we saw in our benchmarks that between 2 points in the same region, for example in Europe, we saw an average of 35 milliseconds latency for each round, and it can go up to 150 milliseconds in average between two different regions. And the last property that we want is what we call concurrent security, where parties should be able to sign multiple transactions, many in parallel, without impacting the security. And it could be with the same key or with different keys. Let's look now at what exists and what are the best-in-class solutions for two-party computation ECDSA. We can see that the first one, Lindell 17, clearly outperforms the others in terms of running time and communication, but it lacks in terms of number of rounds of communication. And we saw in the last slide that this becomes the dominant factor for the whole solution. And all of the other solutions basically lack in one of the properties. And our solution currently stands here. We are able to do it in only 2 rounds with a reasonable amount of communication, of data exchange between parties, and a reasonable amount of time. I would like to deeply apologize to all of you. This talk will mainly focus on the protocol itself, on its description, and on some of the optimizations that we use to make it efficient. I will not go, because of the allotted time for this talk, I will not go into the details, the very technical and theoretical details of it. Let's start by the two-party ECDSA protocol. A quick reminder on ECDSA. It consists in 3 algorithms. The first one is the key generation, simply generate a random scalar and compute the associated points. The signature is as follows, and the verification, well, we just check that this equality holds. Now, what is a two-party ECDSA protocol? So we have 2 parties, let's call them Alice and Bob, very original. They both share a key, and when they call the MPC ECDSA functionality on the message M, at the end, they will get a signature as if it was signed by the recombined key. In practice, this is done using rounds of communication until the end. Our protocol now was designed with cryptocurrency wallet providers in mind, their use case, where we have one server that will serve many clients and will sign transactions with each of them, each having, of course, a different shared key with the server. Now, this use case might make more sense if also we want something that we want the key generation to be fast, because it might happen that a customer wants this architecture while he already has millions of users and he wants to generate wallets for each of them. So in our protocol, the first step is the key generation. Well, it's fairly simple. I will not give the detail of everything here. It's simply an additive share of the key. It's quite common. So let's go to the most interesting part, the signature generation. So the server has its private share x2, the client her private share x1, and of course, after the key generation before, the client also knows the public share uppercase x2 of the server. So the server starts first and generate its nonce k2 and sends to the client these 2 points on the elliptic curve, R2 and Y. Y is basically a proof of knowledge of K2. It's a very simplified version. Okay, it's not the exact one. It's only to understand the whole protocol. Once the client receives this first message from the server, it verifies that indeed the client didn't cheat on that and at least knew K2. And then computes or sample its own nonce K1, compute the 2 associated values R1 and R, and sends them to the server. The server does the same. It verifies the relation between the two, and then it can extract the X coordinate of R, which will become the first part of the signature. From this stage, both the client and the server can now call, before that, the client does the same, extract the X coordinate of R, and compute the 2 following values A and B. And then they can engage in an OLE functionality that will output Y, which is A times X2 plus B. And at this stage, you have to trust me, because R and K2 minus 1 times Y is a valid ECDSA signature on the message M. What is oblivious linear evaluation, or OLE? So we have 2 parties, the OLE oracle in the middle. They both have secrets. Alice has A and B, Bob has X, and at the end they get Y such that Y equals A times X plus B. One security property that we want is that no one learns anything about the secret of the other party. But this is not the OLE oracle I showed you before in the slide. In fact, it took an additional input X, a point on the elliptic curve, that was input by Alex. And the oracle in this case only outputs Y if lowercase x is a discrete log of uppercase X. How to instantiate such an oracle? There are many techniques, and we decided to use an additively homomorphic encryption scheme. So basically, we can compute the encryption of 2 input messages M1 and M2 by combining the encryption of M1 with an encryption of M2. But we also want an additional property of this scheme. We want to be able to multiply it by a constant in such a way that we can compute an encryption of M1 times constant by, again, combining this constant itself with an encryption of M1. There is, and then, once we have these 2 properties, the instantiation of the OLE is quite straightforward using this relation. So now we have 2 small problems, let's say. Which scheme should we use to instantiate it, to implement it in practice? And also how to deal with a malicious party, because this simple scheme here is only secure under the honest but curious setting. So we decided to use PIE encryption. It's quite simple. The key generation is simply computing the biprime n. The encryption is as follows. The decryption is like that. But we also additionally use zero-knowledge proofs that we adapted from CGGMP20. The first one that we'll call PyMod proves that n is a biprime, where each prime factor is congruent to 3 modulo 4. And the second zero-knowledge proof that we'll call PyFac proves that basically no factor of n is larger than the square root of n times a constant. Notice that I haven't said prime factor here. I have only said factor. So, well, it also has an impact on the prime factors themselves. How to instantiate it concretely using PyE? Well, it comes from these two nice properties from PyE encryption that I detailed before. It's additively homomorphic, and we have this external product. Of course, we'll use also the two zero-knowledge proofs. But to instantiate the modified OLE, the one that also takes as input the key on the elliptic curve, we need an additional proof of knowledge of discrete logarithm. It's also something that is fairly common, and it needs to be done only during key generation. And now, second question I asked before, how to deal with dishonest and malicious parties. So I said that we use zero-knowledge proofs during first the instantiation of the OLE, but also a few times during the key generation. Now, we need to generate zero-knowledge proofs, but we need to deal with various algebraic structures. We need to deal with modular integers. We need to deal with elliptic curves. So the go-to techniques in that case is to use integer commitment schemes. And we decided to use the Damgard-Fujisaki one, which is fairly simple, yet really efficient. And we needed it for both the client and the server. Know that the setup phase requires to generate strong primes, and the commitment, verification, and all the associated zero-knowledge proofs require exponentiation. So the last points are pain points in this setting. We'll see in the next slides how we dealt with it. Let's talk now about the additional techniques that we used. We deeply hope that these techniques will be of great interest for the community, and that they will be used to, well, make protocol more efficient. First, I would like to introduce a new class of prime numbers that we call tough primes. Before explaining what they are, let me quickly remind what are strong primes. So they are primes P, such that, so written like this, 2P0 plus 1, such that P0 is also prime. And what we call tough primes, so we need a security parameter, let's call it L. And tough primes are like this. We have a bunch of small primes Pi of size 2L bits, multiply them together by 2 and add 1. And to the best of our knowledge, it's the first time that this new kind of primes is proposed. And we claim that they provide identical security guarantees compared to strong primes in at least all of the contexts that we use in our construction. This claim is backed up by some strong argument in the paper itself. So I invite you to look into it. But what is really interesting about tough primes is their generation. So we used this fairly simple algorithm that gave us the best benchmarks. We first start by sampling a pool of small primes of size 2 times L. And we will randomly pick a a subset of these primes, multiply them together, multiply by 2, add 1, and if the resulting integer is prime, then we find our result. Otherwise, we'll just reiterate. And this gave us this table regarding benchmark. And if we look at, for example, this one, when we try to generate 1.5 kbits integers, prime integers, we got these results using OpenSSL. It took 70 milliseconds for a regular prime and almost 99 milliseconds for a TAF prime. We only have a small factor of 1.4 between the two, while we have a 50x factor when generating regular or strong primes. And it's much better, the comparison is much better between TOF and regular when the bit size of the result is big, and much, much worse when generating strong and regular primes. So we, of course, use TAF primes generation in our protocol, mainly for the Damgard-Fujisaki parameters, both for the setup and for the server and the client. And we saw a 15x improvement in average for both parties. The second technique I would like to talk about is short exponents. So we have this problem, already a well-known problem, called the short exponent discrete logarithm. This is the formal definition. In short, it means that an attacker has a negligible advantage in solving the discrete logarithm when the exponent is small compared to a full-size exponent. Well, I mean small, still of size 2 times the security parameter. And we have this associated problem called the short exponent undistinguishability, simply defined as the attacker cannot distinguish between something that has been generated using small exponent and something that has been generated using full-size exponent. It has been shown in KK04 that SEI can be reduced to SEDL in prime order group. And we also showed that it reduces to this problem in unknown order groups. How do we use short exponents in our protocol? We first used it for the PIE encryption. So a quick recap of how it works. Notice that this part is the more expensive one. Okay, it's a full-size exponent with a randomizer row. And we noticed that if we pick the row such that row can be written as row 0 to the 2 times n, this can become a constant of the PIE parameters. Of course, this relation has to be checked by the client. And then the encryption can be done like this. We can use the same row and only raise it to a random power r of size 2 times L. And, well, this is an improvement in, in the benchmarks because the computation time is linear to the exponent bit length. And of course, the decryption is still possible because the right part of the ciphertext still vanishes once raised to the power of phi of n. And here are the benchmarks that we got for PIE encryption. I should say that only the PIE encryption can be optimized this way. The decryption still needs the full-size exponentiation. So we saw almost 8x improvement for the 2048-bit length, and a bit more than 15x for bigger sizes. And we also used this trick for the Damgard-Fujisaki integer commitment scheme. We used it for all the exponentiation. We just had to be careful about some statistically hiding components of the commitment scheme. And now, the conclusion of my talk. You have to know that this protocol is currently fully implemented, but it's under deployment, and we hope that it will be available soon and deployed at larger scale. Also, we want to improve it even further. Can we reduce the communication and computation? For example, we recently read a paper published last year that suggested that modified the PAE encryption scheme as a PAE plus commitment. So this could definitely reduce the communication and probably also the computation. And we want to dig even further into tough primes, all their applications and implications in the security for other use cases. I hope you enjoyed my talk, and now I'm open to questions.
Thank you very much. Nice talk. Are there any questions from the audience?
So thanks for the nice talk. So the bottleneck for round complexity for threshold ECDSA protocols so far has been sampling the nonce in an unbiased way. So usually it takes a couple of rounds to like exchange commitments, reveal them, and then do something with that. So I'm curious what you do to get around this like interactive nonce sampling. Like, do you have like biased nonces or something? And then also whatever mechanism you use there, can you apply it to previous work, like let's say Lindell or something, to also get the same round complexity?
So, good question. Yeah, I haven't detailed everything about the signing protocol itself, but the first message is not as simple as what I showed. There are additional zero-knowledge proofs in every round. There are also range proofs that are sent just to make sure that the nonce has a given size.
Thank you for the nice talk. I have a question on the more practical side of the setup and the assumptions you have.
Mm-hmm.
You mentioned use a star topology between like your server and a client in a 2PC setting. I'm wondering like how, so in this situation, you're basically using 2PC only to achieve security, right? Like, because the client is still responsible for their key share. So, right? Or am I misunderstanding something?
I'm not sure to understand the question. The client has a key share, the server has
a key share, yeah.
But no one knows the recombination.
Yeah, I'm aware of that. So my question is basically, how come you ended up making a 2PC solution rather than a multi-party solution where you would also get some reliability? Because I imagine a lot in the blockchain setting, the issue is clients, pouring coffee into their laptop or forgetting the seed phrase and things like that.
Yeah, that's a great question.